We are live now.
Okay. So, good afternoon, everyone. Today, we'll be starting our meeting now, and today it will be José Roberto talking about R2 Higgs inflation. Roberto, feel free to start.
Okay. Do you guys can hear me properly?
Yes, we do.
All right. So today I'll be shortly talking about this paper here, Higgs-R square inflation. It's a slow roll study at tree level for this model. It's a very interesting paper. It's something that I was interested in a few weeks ago. Realized that my interest was not leading me anywhere, but fine. It's just basically the motivation for this is the following. R square inflation. Let me find the Lagrangian here. It should be here. Oh, it's not here. Where's the Lagrangian? Okay, I can write it. Okay, so R square inflation is simply an inflation modeled by a Lagrangian of this sort, like that contains a term like this, right? So R square, which is the Ricci scalar. What's happening?
No, you can continue. We're just fixing something here.
Right. This is a very known model of inflation. Okay. It's very well developed. It obeys the slow roll. It works for inflation. We know that the inflaton is a scalar field. And it works as inflation because when we do R square gravity, we get one additional degree of freedom, which is the scalaron. The scalaron is a scalar field that appears because R square involves fourth order derivatives in the metric. So since the metric supposedly is the graviton field, you get this additional scalar field to account for this additional degree of freedom that you get from the fourth order derivative. Well, you know that this works very well, and then there are some works that try to make the Higgs the inflaton, which is a good idea as from my point of view, like because if you think about it, the inflaton has to be a scalar field. The most natural scalar field we have is the Higgs.
Roberto, can you please zoom in a little bit?
Zoom in?
You don't need it. It's okay.
Oh, okay.
Okay. And since the Higgs is our natural, as far as we are aware of, a fundamental scalar field, we can think about it. And people have done this type of work and showed that if the Higgs couples non-minimally, it's important that the Higgs couples non-minimally to gravity. Non-minimally, I mean, it has a coupling of this form with the Ricci scalar. Because if it couples only minimally to gravity, it doesn't work. It works. Then if you couple non-minimally, it will work. So in this paper, these three authors, especially Starobinsky here, is here. Where is it? So, this paper here specifically, they investigated this behavior of the Higgs. Okay. Oh God, I opened the wrong paper. That's why I was actually looking. So just a second. That's why I was not finding the Lagrangian. Just a second here.
To the people who organized, Priscilla said that she's not getting access to the meeting, probably because of the issue with the email. I think she doesn't have an email from UFRN.
Just a second. I'm opening the correct paper here. Was looking for the Lagrangian. That's why I didn't find it. Okay, just have to open on my own computer. It's not opening on my tablet. Sorry.
Well, I think he's in the first floor.
Farinaldo is asking, is he on the first floor? You, Roberto.
I am
Yeah.
on the first floor. Why?
don't
I am
know.
on the same office as Clarissa was.
Yeah, I know.
Her name was on the door.
Yeah.
It's the same office Carlos Diagona used to be.
Okay, that's the correct paper. You see why my confusion happened? It's the same name. Open the wrong one. There you go. So, all right, let's go. So the motivation is still the same. It's just a different analysis. There you go. That's the Lagrangian I was looking for. Usually you have all these terms. Here, people try to investigate. They have the Ricci scalar term, which is the Isaac-Hilbert action term, and then you have this scalar field coupling non-minimal. Can you please mute your microphone because I'm hearing my own voice?
Sorry.
Please. All right, thank you. So
A little.
you have the
Yeah.
non-minimal coupling, as I was talking about. The thing is, what they do here, they do not consider this necessarily as the Higgs. You see that this is not a Higgs doublet. It's not a doublet at all. It's more of a singlet, if you think about it. And then you have the R squared term and the quadratic term from the supposedly Higgs. After you do a conformal transformation, which is this one, a local conformal transformation, which corresponds to the Weyl transformation, you get this corresponding Lagrangian here, in which you have the linear term, which is Einstein-Hilbert action. The goal to do this is to go to a frame, which is the Einstein frame, in which the equation of motion for gravity is not coupled. It's not coupled. It's just the Einstein equation, natural one. And you get a kinetic term for this new field, which is the scalaron as I was talking about. You have the kinetic term for the chi field, which is supposedly the Higgs, and you have a potential, which is described here, which acquires these exponential terms because of the Weyl transformation. Now, a funny thing happens is, well, if you pay attention here, the kinetic term for the chi field is not canonical. So that is an indication, and there is no transformation at all that can make it canonical, right? If you perform an entire transformation, you will not get it to both of the kinetic terms to be canonical. That is an indication that the field space is not flat; it has curvature. So what you do is you induce the metric on the fields, which is this metric here. It's very straightforward. And then you have two fields, 2 degrees of freedom, and you have a non-flat space for the fields, non-flat vector space for the fields. So this has some consequences because then when you're doing something like this, you have to use something called multi-field covariant formalism, which you track the evolution of the fields in their spaces, and it's a little bit different than what you usually expect when you have just canonical kinetic term fields. What they do after this is very straightforward. They just simply go around perturbing the fields. So they do in a covariant way with phi A, and they use the flat gauge. Okay, the flat gauge is one choice of gauge for perturbations in the metric. And then they get the equations of motion. So this is the Friedmann equation. You have equations of motions for the field, for the background field, and for the perturbation of the field, which drives the perturbation, which will then subsequently generate the perturbations we see in our universe today. So as usually, he defines a few things here. Since this is non-flat, it has curvature, you live in a specific space. You have the metric, then you have the Christoffel symbol, and you will also have this is not the Einstein tensor. This is the not the Ricci tensor as well. Forgot the name of the guy, but okay, this is a tensor. You got a tensor for curvature because of the induced curvature in the field space. And of course, they analyze this. So the goal is to derive some things to try to find what exactly it is that is happening when you have a mix of these two guys. And then they analyze the slow roll inflation, because you have to have slow roll. And then they derive the curvature perturbations, because this is something we know from WMAP, and you have to make sure that it agrees with observations. So they choose a typical value of lambda equals to 0.01. So in the standard model, lambda is 0.14, if I'm not mistaken. So you have the freedom here to choose it differently, because you introduce a new scalar field, so things change a little. And actually, as a good fact, the Higgs potential is not stable, which means that what we expect from the Higgs, that if we go to high enough energies, we do realize that the potential at some point crosses zero and goes to a negative value, and that means that we are living in a metastable vacuum. But when you introduce a new scalar field, you can make it stable. Okay, so this new scalar field from the scalar can actually make it stable. There are other papers that study this specific thing, but that's another motivation for introducing this new degree of freedom. Okay, so there are some features. The first one is that this potential is invariant under this, I would say, parity transformation on the field. And you also you can calculate the mass of the Higgs. They call the Higgs, but it's not the Higgs, the Chi field here, by taking the second derivative with respect to Chi on the field. You find there are two different regimes. It's proportional to psi when Chi is small, and you get a negative overall value because psi is greater than zero. Okay, this exponential is always greater than zero, and then you get like smaller than zero value. But if for large value xi, you have an overall positive value that is not negative at all. That indicates that you have a global minimum of the potential. This global minimum is very important to the behavior, you can see here, because you have to slow roll the field. One of them have to slow roll. So you can induce inflation. So you can induce like the exponential expansion of the universe. And you have to have a minimum so the fields will relax to it, oscillate, and subsequently decay into standard model, causing the reheating. So here you have two examples. They plotted with respect to the psi, different values of psi. The basic difference there is that you flatten out the direction of psi. So if you get a small enough psi, you probably have a greater slow roll than if you have a great psi. That is very intuitive. The psi is exactly how strong the Higgs couples to gravity, right? So the stronger it couples, the more it will interact. So they do this lower inflation. Here I'll go very fast because this is just mathematics. What happens is they analyze it in terms of not the fields itself, but in terms of directions of the fields, which is the tangent direction and the normal direction in field space. So they define a different vector space to do this analysis. And the consequence of this is that these slow roll parameters are a little bit different. So you have the usual slow roll parameter here, epsilon, that has to be very small. But the eta slow roll parameter, it's no longer a scalar, it's a vector on this specific space, which you can decompose here into a parallel direction, which is the tangent one, and a normal direction. So as usual, the eta parallel is the one that has to be very small because it's the one that detects the slow roll, has to be in the normal direction of the field, but the parallel one. But the normal one doesn't have to be small at all. You don't have any bounds on it. The only bound you can find is on, so this is the adiabatic evolution, so the angular velocity of the field. The only bound you can find is from the adiabatic condition, right, of the inflation, right? Now they do another change of variables, which is now they consider the moving curvature perturbation, the iso curvature perturbation here. They do this to specifically get something that's very interesting from this model, that after you do this change of variables, you find this Lagrangian here, okay? That you see that you have one degree of freedom that has mass and one massless degree of freedom. Okay, this R, which is the curvature perturbation, doesn't have mass, right? So essentially what you get from starting from that point, with the mix of Higgs and the R square, you find that you have evolution where you have one massless and one very massive degree of freedom. The mass, of course, is defined as the second derivative of the potential. It's a very massive thing. You can find it here. So it's defined in terms of this u and n, which is the second derivative in terms of the normal direction. And this blank mass and all along. So this is very interesting because this is a massive one. This is massless. That means that you can actually integrate out f, and you find an effective Lagrangian, which is this one. This is the action, but every time I talk about Lagrangian, I talk about this thing inside. Once you integrate it out, and the actual thing that's happening is you are changing the speed of sound in the plasma. So instead of having 2 degrees of freedom that we started with, the Higgs and the scalaron, you actually end up with 1 degree of freedom and a change in the speed of sound. Okay, this is interesting, but actually points out that effectively everything you do, you will get to one of the limits of the 2 models. Okay.
Zé,
Hi.
can I make a question right now, or would you prefer to?
Yeah, you can ask.
You are always saying Higgs, but it's the chi, right?
Yeah, Higgs is the chi. It's just a scalar field that's supposedly the Higgs.
Sorry, I lost. It's kind of a doublet. What is it?
No, it's a scalar.
A
You can
scalar,
think of
okay.
it, the Higgs in the unitary gauge. There you go.
Okay, but you showed kind of the coupling, but if you have a kind of a bigger coupling to the gravity, the mass should be bigger, right? Or not?
The mass of the...
Yeah.
So Xi is not the coupling that directly relates to mass. Xi is the non-minimal coupling, which is the coupling with the curvature here. So it only relates to this. Right? It's just a conformal coupling. See, doesn't really have anything to do with the mass, because usually when we talk about it, in my mind, it's usually because of this that goes with the energy, right? This is just a conformal coupling that appears. It's mandatory. It has to appear. This has to appear. If you have a theory that you have gravity and you have a scalar field, this coupling will appear. It's required by renormalizability. Okay.
Okay.
So, this is
okay.
just...
I'll try to understand that. Another question: Have you ever seen people trying to put gravitons on that, coupling to gravitons?
Well, when you try to do Higgs inflation, you try to escape the direct coupling of the Higgs with the graviton that comes from the minimal coupling, right? Which is you expand this metric in terms of a background plus graviton, and this does not give you the correct predictions for inflation because the quadratic value of the potential of the Higgs is very small. Sorry, very small, yes. So you try to escape it. So the coupling is only to the curvature tensor, which you can think of it as trying to couple with gravity, but I have never seen this treatment.
Yeah, because if it couples, it could generate gravitational waves, just like showed us today.
Yeah. This generates gravitational waves. So this paper doesn't really talk about it, but there are papers that talk about this. I'm not sure how it works, but it does. I've seen it.
We talk about that later. Thank you very much.
Yeah, sure. I was dying. Okay. And then they just relate the power spectrum here for curvature perturbation. This is the what we get, and the one of the important parts, something that we get from observation, is the scalar to tensor ratio. Okay, and the scalar index here. That's 2 things that we know from observation. Okay, and then they do a little bit of predictions for observations, and they plot this weird figure here. I have no idea what it is. It has no. It should be NS, like the scalar index and the scalar to tensor ratio, but I'm not entirely sure what's happening here because they don't explain it very well on the paper. The figure is just thrown out there, just not very well explained.
Know what the axes are?
Sorry? Carlos?
Know what the axes are?
No, I have no idea. They don't say it.
Great. So
It's supposed to be the scalar index and the scalar to tensor ratio, but it's a bit weird. All right. So the point of this is that it agrees with observation. Okay. The point of this part here of the paper that it agrees. If we go further to the effective R-square inflation, is basically them analyzing limits on the theory. So they plot this one here. That's the M factor, which is the mass of the scaleron technically over the Planck mass with the non-minimal coupling. So basically what's happening here is that if the non-minimal coupling is below 1000, it behaves constantly, the mass, but if it goes over 1000, the mass has to increase to ensure slow roll, which is because of the plot I showed before. If the psi increases too much, you have a change, very big, very large, on the potential. So you have to compensate by increasing the mass of the scalaron, or this mass term here that you can interpret as the mass of the scalaron, or just an effective mass of something. So this is them explaining this, and them explaining their limits, which is basically saying that there are two limits for this theory: the R-square inflation alone and the Higgs inflation. The R-square inflation alone, you get if you set the quadratic coupling to 0, and the non-minimal coupling to 0. It's very straightforward. And then you only get the Higgs inflation if the mass of the scalaron is really, really high, which is basically saying that you can integrate it out. It's irrelevant at any energy level because it's really high. Infinity doesn't exist necessarily in physics, just basically saying that M is really, really large and it's irrelevant at the point of inflation. So this is the paper. This is it. This is what they're saying here. I was mainly interested because of the calculations. So any questions?
Okay. Just a minute. So we're open for questions now. Do you guys have any questions? So in that case, let's thank the speaker.
Do you have something else?
Huh?
Do you have something else?
Does Roberto have something else?
No. We have.
No, I don't.
Actually, we have something else, but Matheus told me that it will not be going live. It's Victor's presentation now.
Okay.
Yeah, I'm going to talk about a presentation from another person. So
Let me just finish the live real quick. It's just click here. I think on stream.